right, let us once again perform the whole enchilada. That is, let's diagonalize a matrix, not knowing any of the information from the beginning about any of its eigentheory, any of the spectral results about this matrix. Let's do the whole enchilada. But this time we're going to do it with a complex matrix, but this complex matrix will be Hermitian. If we take the conjugate transpose of A, we do get back A here. And so when we diagonalize this, we can actually do a unitary diagonalization. And so that's what we're going to try to do here. And so this will take a little bit of effort because there's a lot of things going on here. So let's begin by looking for the eigenvalues of this Hermitian matrix. By the spectral theorem of Hermitian matrices, we can anticipate that these vectors, the eigenvalues, are going to be real. So how do we do that? The characteristic polynomial of this matrix, remember, is the determinant of A minus lambda I. We don't know what the lambdas are yet. We'll treat it as a variable. And so we're taking the determinant here, 2 minus lambda, 1 plus I, and then 1 minus I, and then we get 3 minus lambda. As this is just a 2 by 2 matrix, we can take the product of the diagonals and subtract them. So we get 2 minus lambda times 3 minus lambda. And then we're going to subtract from this 1 plus I and 1 minus I right there. So FOIL out the 2 minus lambda with the 3 minus lambda. We end up with 6. We're going to get minus 2 lambda minus 3 lambda plus lambda squared. Do be careful on the complex arithmetic if you haven't had as much practice with that. You can FOIL that thing out, in which case you would get something like 1 minus I plus I, and then you're going to get negative I squared, which is actually plus 1, since I squared is negative 1. You'll see some combination of things like the negative I plus I, they cancel. The negative 2 lambda will combine with the negative 3 lambda. And so we end up with 6 minus 5 lambda plus lambda squared. And then we get a minus 2 right there. Putting this all together, our characteristic polynomial is lambda squared minus 5 lambda plus 4. And our goal, of course, is to factor this thing. We want factors of 4 that add up to be negative 5. We can take lambda minus 4 and lambda minus 1. And so then our eigenvalues are going to be 4 and 1, which, as I predicted, I mean, because there's no soothsaying that happened right here. I didn't have to look at the bones of a dead shrew or anything. We have a Hermitian matrix. Its eigenvalues necessarily have to be real. So we get these numbers 4 and 1. So now we have the eigenvalues. So what we want to do now is proceed to compute the eigenspaces. That is, find a basis for each eigenspace. So we're going to consider, we want to look for the null space of A minus 4I. We'll do that over here. And then on the other side, we'll look at the null space of A minus I, 1I there. And so consider what's going on there. So we have to first take the matrix A minus 4I, like so. And so as a matrix, this will look like 2 minus 4, which gives us a negative 2, 1 plus I, 1 minus I, and then we're going to get 3 minus 4, which gives us a negative 1 right here. Did I do that one correctly? I think so, yeah. Let's see. Yes, that's fine. And so notice here that you have a 2 by 2 matrix, and we know that this thing is singular, right? Because after all, since 4 is an eigenvalue, this matrix is going to be singular. So we could actually do ourselves a little bit of a benefit for us, that we know that the second row is going to basically just vanish away because it has to be a multiple of the first row. Otherwise, this thing would be a non-singular matrix. Since it's singular, we know this thing can row reduce to be, I'm going to times the first row by negative 1 as well. So this will row reduce to be 2, 1 minus I over 0, 0. And the reason I do that is then you can divide by 2 if you want to. But we have this relationship. If we think of the associated homogeneous system of equations here, we have that 2x1 is equal to 1 plus I x2. And so if you pick something like x2 equals 1, you end up with, well, actually, I think I'm going to go the other way around. I actually want to solve for x1 right here. And so you're going to get 1 plus I over 2 times x2. So if you said x2 equal to be 1, right, then you're going to get this vector v1, which is given as x2 is set to be 1, and then the first one will be a 1 plus I over 2, like so. And like always, if you don't care for the fractions, you could always factor that thing out, the 1/2 that is. And so you end up with 1 plus I and 2, which is kind of what I was hinting towards earlier. And you can just ignore this scalar because, again, we're looking for a basis. We don't need a specific vector. So we can take this vector v1 to be 1 plus I and 2. This is perfectly good right here. As we are trying to look for a unitary diagonalization, we do have to normalize this thing. If we take the length of v1 here, you'll end up with 1 plus 1 plus 4 all inside the square root. You just square the real imaginary parts of these things individually and add them together. And so we end up with the square root of 6, which then tells us our vector u, the eigenvector we want. This is a normal vector here. It's how you have the length of 1. We're going to get the vector 1 over the square root of 6 times 1 plus I and 2. So this is our vector u1 that we're going to use in our forthcoming unitary matrix. Let's go back and repeat this process for the eigenvalue 1. So same basic idea. We have to look at the matrix A minus I, which that ends up giving us -1. We get -1. I'm sorry, I think I did that one backwards there. Peeking at what we did before, right? Because I mean, after all, if you're not sure what to do at this stage, just look at the determinant you did before and just plug in lambda equals 1 there. Of course, don't actually take the determinant. So we get 2 minus 1, which is 1, 1 plus I, 1 minus I, and then 3 minus 1, which is a 2. So this is the matrix we want to row reduce. And kind of like I said before, we could use the fact that because we have a 2x2 matrix and we know it's singular, the second row we don't need it because it has to be a multiple of the others. This kind of helps us avoid some of the arithmetic with the complex numbers. We ended up with 1, 1 plus I, and then 0, 0, like that. And so then in terms of our free variables and dependent variables, we get x1 is equal to -1 plus I x2. And so we can take as a vector v1, we'll just take x2 to be 1 again, and so we get -1 minus I right there. That gives us a pretty good eigenvector. No fractions to have to worry about. We can't really avoid the imaginary numbers whatsoever. But be aware as we normalize this thing, when you take the length of this vector, this is not v1, this is v2 now. When you take the length of v2, you're going to get 1 squared plus 1 squared plus 1. So the length of this vector is the square root of 3. Again, you just square the real imaginary part individually and add those all up. And so then u2 is going to be the vector 1 over the square root of 3 times -1 minus I all over 1. And you can switch that with a negative if you wanted to. I think we'll be content with the vector that's in front of us. So now that we have u1 and u2, our matrix A, the original matrix A, can be then factored as P, D, P star. We're looking for a unitary factorization here. Now the matrix P will take as its columns u1 and u2. The diagonal matrix will take the two eigenvalues we had as its diagonals. And then as we're taking the conjugate transpose for P, our matrix is going to look like u1 star, u2 star. So those are going to be row vectors right there. And so if we plug in the information that we have now found, we get the following. Give yourself some space here. So u1 we saw before, we're going to get 1 plus I over the square root of 6. We're also going to get 2 over the square root of 6. Don't feel any desire to rationalize those denominators. It's not going to help us out any bit right here. And then for u2, we're going to get -1 minus I over the square root of 3. And then we're going to also get 1 over the square root of 3. So this is our matrix P. Our matrix D will be the eigenvalues we had before, which is 4, and 1. Make sure you go in the same order that you put the eigenvectors. And then for P star here, we take the conjugate transpose of the first matrix. So rows become columns, and make sure you take conjugates. So you get 1 minus I over the square root of 6. So we took the conjugate of that. You're going to get 2 over the square root of 6. That was a real number, so therefore the conjugation did nothing. Next, you're going to get negative 1 plus I over the square root of 3. Notice how I took the conjugate right there. And then you get 1 over the square root of 3 right here. And so you now see in front of you we see the orthogonal diagonalization of this matrix, right? And you can multiply this thing out and verify that this is in fact a correct factorization of the original matrix right there. And so this is, again, the whole enchilada, but with the extra benefits that we did some complex numbers this time, and we, in fact, got an orthogonal. I take that back. We had a unitary diagonalization, which is the complex counterpart of an orthogonal diagonalization.